we're going to talk about positrons. And I showed this picture before. Positrons, charged particles, electrons, charged particles. Gamma ray comes in, hits a nucleus. The gamma ray converts its energy into matter, makes an electron, makes a positron, an anti-electron. Okay? The electron and the positron fly off, and they go in these like circular arcs. Why do they go in circles? There's a magnetic field which is present, so the particles are circling around the magnetic field lines. The magnetic field in this picture is out of the board. Given that, which of these particles is the electron? Which one is the positron? Okay, and I'm going to call a name out of the box and ask a person to answer this. Which is the electron? Which is the positron? And there's a bonus question. I'll take that piece of paper and write +1 on it. The bonus question is this. Why did the circles get smaller? Because you can see it's winding down. Why does that happen? Talk to your neighbors about this. I'm going to call a person's name out of the box in about 45 seconds. We're going to use the right-hand rule for this, okay? So if I have a charged particle which is moving to the right, and they both start moving essentially to the right, right? Charged particle is moving to the right. What's the direction of the magnetic field? Out of the board. So if you're a positively charged particle, the direction of the force you feel is downward. Okay, or using your velocity, field, force, it's going to feel a force downward. So if you're a positively charged particle, you'll start to curve downward and then continue a spiral. So which one of these has a positive charge? B, because it starts bending down and then it goes in a circle like so. So B is the positron. A is the electron. Excellent, excellent. Now as the particles travel, they're making an ionization trail that bubbles form on. This is a bubble chamber photograph. How come the circles get smaller? Okay, let's think about it. What could change as the particle travels? Mass doesn't change. Charge doesn't change. What could change? The speed. Oh, what would happen to the size of the circle if the particle moved more slowly? It would get smaller. So the circles are getting smaller because speed is getting smaller. And they're slowing down because they're making ionizations as they go along. As the particles move, they ionize atoms. As they ionize atoms, they're giving up energy. As they lose kinetic energy, they slow down. And so the circles will get smaller. If you have a gamma ray, we talked about this last time. We did a calculation for it. A gamma ray can produce an electron and a positron. So if you take an electron and a positron and you bring them together, they completely annihilate. They completely annihilate, and they produce energy. So I have an electron and a positron. I bring them together. They completely annihilate. The only thing left over is energy. But I can't make one gamma ray. I have to make two gamma rays. And here's why. The two completely annihilate, and there's this like flash, and two gamma rays come out, and the gamma rays go in opposite directions. And the reason is this. Photons don't have mass, but they do have momentum. And I have to conserve momentum. The initial momentum of the electron and the positron is 0 in this case. And so the momentum of the photons has to be 0, and so they have to go in opposite directions. So I can't make just one photon. I have to make two. Where does the energy come from to create the photons? The mass energy. And so if I'm going to write down the energy of the two gamma ray photons, I'm going to use the most famous equation in the world. The energy of the photon is equal to m times c squared. For one photon, how much mass do I use here? There's two particles that come in, and they have the same mass, right? They both have the mass of the electron. And I produce two photons. So each photon corresponds to the mass energy of how many particles? One particle. Because two particles come in, two gamma rays go out. Each gamma ray gets the mass energy of one particle. So what do I put in for m in this equation? Mass of the electron, which we know that's just 9.1 times 10 to the minus 31st kilograms. And c is the speed of light, 3.0 times 10 to the 8th meters per second. And if I solve it out, I get 510 kilo electron volts if I convert it to electron volts, which I think we want to. Now here's why that's useful. You can use this in a diagnostic technique called positron emission tomography. There's short-lived isotopes, and here's two of them, that decay. They do a beta plus emission. They decay by the emission of a positron. To make one, they're a trick to make. You can make neutron-rich isotopes in a nuclear reactor because you split the neutron-rich elements apart and you end up with things which are neutron-rich. But if you want to make proton-rich isotopes, you make them in a cyclotron. You take a charged particle, you get it up to a high speed, and you slam it into something else and see if it sticks, basically, is what you do. And you can make these proton-rich isotopes. And if you take this one, proton-rich fluorine-18 decays to oxygen-18 with the emission of a positron. The positron comes out, kind of like cruises around, slows down, stops, annihilates with an electron, gives off 2 gamma rays that move in opposite directions. This person is sitting with her head inside this giant detector. Every time a positron decays inside her brain, it hits an electron, decays, produces 2 photons. They go in exactly opposite directions. And so you can tell where they came from. You can tell where they came from. You can tell that they had to come from a line that connects these 2 detectors. And you can also tell this. You can tell where along the line it is because I can measure when did it hit here, when did it hit here. If it hits this one first, it's on this side of the head. If it hits this one first, it's on that side of the head. How do they get in the brain? That is a really good question. You take it and attach it to glucose.
Oh, it's the same thing.
Same thing. Attach the fluorine to glucose. The brain takes up glucose, and then it decays. And then you can tell where was the fluorine in a person's brain. And you can pinpoint it very exactly. You can also use oxygen-15. Check out this half-life, 2 minutes. So if you want to use this, you have to live next door to a cyclotron. You can't live on the other side of town from a cyclotron. You're going to be in the next room. Okay. Here's an example of a PET scan, positron emission tomography. The person's given glucose that's tagged with this beta plus emitter. Take it up the brain, then you do a scan and map out where was the glucose taken up. And you're showing the metabolic activity of the brain. Now remember, metabolic activity of a normal brain, something like this. Metabolic activity of this person's brain, I can see a ring here, but I see a real bright spot. That's not normal metabolic activity. That's a tumor. Very, very high metabolic activity. So it says there's a lot of metabolism going on there, and it's not healthy. That's not a good thing. And that's due to the presence of a tumor. Okay? And it's a really, really good technique to isolate things like that. It wouldn't necessarily show up on a CAT scan. It might look normal. But it shows up here, and you can say it's just using a lot more glucose. You can also use PET scans or PET scans to tell what parts of the brain are used for different activities. And here's an example. This is a great one. So people were given oxygen-15, which has a half-life of 2 minutes. And since it decays so quickly, it turns out you can have much less radiation dose to a person. The oxygen-15 is just 2 minutes. It's very quickly going to go away. And oxygen is only going to be taken up by your brain when your brain's working, right? So give you this, stick in the PET scanner, and then someone's talking to you. But they're talking to you in Polish or a language that you don't understand. You're sitting there in the scanner going, whatever, whatever, whatever. Here's the parts of your brain that are active. The auditory cortex. I mean, the part of your brain that hears sounds. But then someone comes in, same volume, talking in English, then more of your brain is active. Because that's the parts of your brain that interpret speech. And so you can tell where they are. And you can use this to localize functional areas of the brain. You can say what they're actually doing. Because these gamma scans, these PET scans, image function, not structure. Very, very cool. Very, very cool.